We have now reached the tipping point of accelerated computing. We have now reached the tipping point of generative AI. This is going to touch literally every single industry. Software is no longer programmed just by computer engineers. Software is programmed by computer engineers working with AI supercomputers.
Supercomputers have made a significant leap forward with powerful artificial intelligence, revolutionizing software development. Engineers and supercomputers are now collaborating to achieve feats once thought impossible, an exciting yet unsettling prospect. At the heart of this transformation is the immensely complex H100 computer. With these rapid advancements, what happens if these machines start acting autonomously? Let us explore how small humanity appears when faced with the record-breaking 5,000% expansion in the power of the most advanced AI chip. Inside the H100 revolution, a significant shift has occurred in the ever-evolving landscape of technology, marked by the rise of accelerated computing and the integration of artificial intelligence into the very fabric of software development. This shift has transformed the role of computer engineers, who now collaborate with AI supercomputers to push the boundaries of what machines can do. The atmosphere in the tech industry is charged with a mix of anticipation and skepticism, as these advances promise to reshape every sector imaginable. At the heart of this technological revolution is the H100, a computer that has been heralded as a game changer. Its production process is a marvel of modern engineering, involving a system board that houses 35,000 components and is powered by 8 advanced Hopper GPUs. This complexity is not just a showcase of human cleverness, but also a humbling reminder of our growing dependence on high-tech machines. The H100 itself is a behemoth, weighing between 60 to 65 pounds. Its assembly requires robotic precision due to the high-pressure demands of fitting its numerous parts perfectly together. Ironically, despite its capabilities, the computer cannot be assembled without the aid of other machines. This dependency underscores a broader theme in modern technology: the creation of devices that are as needy as they are powerful. With a staggering price tag of $200,000, the H100 replaces entire rooms of older computing equipment, earning it the title of the world's most expensive computer. The manufacturers tout economic efficiency with a twist: buy more to save more, a pitch that might raise eyebrows considering the upfront investment involved. Beyond its commercial appeal, the H100 is pioneering in its inclusion of a transformer engine, setting new standards for AI-driven computing performance. This leap forward comes at a time when the computer industry is facing a critical junction. The traditional reliance on CPU scaling to improve performance has reached its limits. The familiar pattern of gaining significantly more power at the same cost every 5 years has come to an abrupt halt. This stagnation has resulted in 2 major trends within the industry. The first is a pivot towards new technologies like the H100 that promise to continue the trajectory of rapid advancement. The second is the increasing embrace of AI as not just a tool, but a partner in creation, reflecting a deeper integration of technology into the creative process itself. The promise of these technological advances is immense, suggesting a future where computers are not only tools, but collaborators capable of driving innovation to new heights. Yet, this future also brings challenges, as the increasing complexity of technology could potentially lead to greater complications. As this narrative unfolds, the tech industry must navigate these waters carefully, balancing innovation with a critical awareness of the broader impacts of these powerful new tools. A world rapidly transforming through the innovations of technology, the introduction of deep learning marked a significant turning point. This method revolutionized the way software was developed, coinciding with the rise of accelerated computing and generative AI. Together, these advancements reshaped the entire computing landscape, a process that had taken nearly 30 years of meticulous development and refinement. This shift was akin to replacing old, bulky television sets with sleek, modern LEDs, a stark improvement in efficiency and output for the same price. It underscored the importance of GPU servers, known for their high cost, but essential for modern computing. In this new era, the focus shifted from individual servers to the optimization of entire data centers. Building cost-effective data centers became the new challenge, overshadowing the previous goal of optimizing individual servers. Attention to individual server performance sufficed. However, the evolution of technology and increasing demands meant that the broader infrastructure, the data center itself, became the critical focus. Compact, high-speed data centers were now the goal, rather than merely large ones. An illustrative example of this was in achieving specific workloads dubbed ISO work. The improvements brought by accelerated computing in this area were nothing short of transformative, offering a clear before and after picture of technological evolution. NVIDIA's GPUs, originally perceived as limited to specific computational tasks, had proven themselves to be versatile and indispensable. They now played a pivotal role in modern computing, pushing forward the capabilities in generative AI and beyond. The widespread adoption and high utilization rates of these GPUs in every cloud and data center pushed these facilities to their limits, highlighting the immense impact and necessity of GPUs in contemporary computing setups. This new age was defined not merely by the hardware used, but by the limitless potential for innovation and improvement. As GPUs continued to evolve and adapt, they propelled the computing industry forward into an era where technological boundaries seemed ever expandable, promising a future of endless possibilities and advancements. Now, let's see how NVIDIA AI is changing technology. The rise of AI supercomputing. A revolution was underway with the transformation of the GPU, now designed to excel in tensor processing, a core element of AI operations. This revamped system, known as NVIDIA AI, was engineered to manage an entire spectrum of tasks, from initial data handling through to training, optimizing, deployment, and inference, integrating all phases of deep learning that underpin modern AI. These GPUs were interconnected using a technology called NVLink to enhance their capabilities, amalgamating them into a colossal single GPU. This setup was further expanded by linking multiple such units with InfiniBand, creating vast, powerful computing networks. This strategic expansion was not just for show, it played a pivotal role in enabling AI researchers to push forward with developments in AI technology at an astonishing pace. With each 2-year cycle, the field witnessed significant leaps, propelling the technology forward, with the promise of more groundbreaking advancements on the horizon. Looking ahead, it was envisioned that every major company would soon operate its own AI factory, dedicated to creating its distinct type of intelligence. Previously, intelligence creation was an inherently human endeavor. However, the future landscape was shaping up differently, with the mass production of artificial intelligence becoming a norm. Each company was expected to establish its AI production line, significantly altering the traditional business operations. The rise of AI was seen as the next monumental phase in computing for several reasons. Using AI and accelerated computing, technological advancements had enabled the speeding up of computer graphics processing by an unprecedented 1,000 times in merely 5 years. Moore's law, which once posited that computing power would double approximately every 2 years, now seemed almost obsolete in comparison. The implications of increasing computing power by 1,000,000 times in 10 years were profound. Such immense power opened up possibilities for applying computing technology to previously inaccessible fields. The widespread enthusiasm for these advancements was justified. Each new computing era had historically enabled previously impossible capabilities, and this era was proving to be no exception. What set this era apart was its ability to process and understand diverse types of information, not just text and numbers. This capability made modern AI invaluable across various industries. Moreover, the new generation of computers was designed to adapt to the programming language or style used, striving to decipher the user's intent through extensive, sophisticated neural networks. The narrative unfolding was one of vast technological strides alongside an evolution in industry, painting a future where companies not only adapted to, but fully embraced the surge in computational power to redefine possibilities. This era promised not just technological growth, but a redefinition of global industrial landscapes. Each new advancement seems to arrive with a wave of grand claims about its potential. One of the latest developments is a language model that boasts of being so intuitive that practically anyone could master programming simply by giving voice commands. The claim was that the divide between those who were tech-savvy and those who weren't had finally been bridged. However, beneath the surface of this seeming simplicity, the complexities of power dynamics in technology persisted, largely unchanged. Old software applications, ranging from basic office tools to more complex web environments, were now being marketed as rejuvenated by the integration of artificial intelligence. The prevailing message was clear. There was no need for new tools when the old could simply be updated with AI capabilities. Yet, the reality of these enhancements was not as simple as it was portrayed. Adapting traditional software to function with AI often required significant modifications to their foundational architecture, sometimes necessitating complete overhauls. The NVIDIA Grace Hopper AI Superchip served as a prime example of this new technological era. This processor, packed with nearly 200 billion transistors, was not just a component, but was heralded as the cornerstone of future computing. With 600 gigabytes of memory designed to seamlessly connect the CPU and GPU, it promised a new level of efficiency by reducing the need to transfer data back and forth. This superchip was touted as a revolutionary solution for handling extensive datasets with unprecedented speed and efficiency. However, it also posed questions about the monopolization of power within the tech industry. What would the concentration of so much computational capability in a single chip mean for market competition and innovation? While the discussions frequently highlighted the capabilities of such technologies, they seldom addressed the environmental impacts and ethical considerations of producing and operating these advanced systems. The vision for the future did not stop at a singular chip. Plans were laid out to link multiple Grace Hopper chips together to form a formidable network. Envisioning a setup where 8 of these chips were connected at extraordinary speeds and organized into clusters, the structure was designed to scale up by interlinking these clusters into a massive computational network. This ambitious design showcased an impressive level of connectivity and operational speed, but also underscored an insatiable drive for more power and efficiency, which often overshadowed the underlying issues of complexity and opacity in such expansive systems. Next, we look at the impact of these technologies on people. The hidden costs of supercomputing. As these supercomputers expanded and interconnected, the individual's role seemed to diminish. The notion of being a programmer was shifting away from innovative coding towards maintaining and feeding data into these vast, powerful systems. The narrative that AI could enhance every existing software application was appealing, yet it seemed more likely to reinforce existing technological hierarchies than to disrupt them. While a marvel of engineering, the Grace Hopper required a discerning evaluation. Its capabilities were undoubtedly impressive, yet it was crucial to consider who benefited from these technological advances and at what societal cost. The transformation of the technological landscape was not merely a matter of hardware and software advancements, but involved significant social and economic shifts. As these changes unfolded, there was a risk that individuals could become mere bystanders or even subordinates to the formidable machines that their own ingenuity had created. Let's visualize what this looks like. Imagine a giant setup stretching over your entire infrastructure, made up of 150 miles of fiber optic cables, enough to span several cities. Inside, 2,000 fans blast air powerfully, circulating 70,000 cubic feet per minute, which could refresh the air of a large room in just moments. The total weight? 40,000 pounds, comparable to 4 adult elephants, all packed into the space of one GPU. This enormous machine is the Grace Hopper AI supercomputer, named to inspire thoughts of innovation and pioneering work. It's a single giant GPU, and building it has been a massive undertaking. NVIDIA is currently assembling this giant, and soon tech giants like Google Cloud, Meta, and Microsoft will use it to explore new areas of artificial intelligence. The DGX GH200, its official name, represents NVIDIA's ambition to push beyond the current limits of AI. NVIDIA aims to transform data centers worldwide into accelerated centers equipped for the new era of generative AI over the next decade. To address these varied needs, NVIDIA has introduced the NVIDIA MGX, an open modular server design created in partnership with several companies in Taiwan. This new server design is a blueprint for the future of accelerated computing. Traditional server designs, made for general computing, don't meet the needs of dense computing environments. The MGX design is a model of efficiency, combining many servers into one powerful unit. This not only saves money and space, but also provides a standardized platform that will support future technology like next-generation GPUs, CPUs, and DPUs. This means that investments made today will continue to be useful in the future, fitting new technologies with ease and keeping up with market demands. The chassis of the MGX serves as a base on which different configurations can be built, tailored to meet the diverse needs of various data centers across many industries. This design flexibility is crucial in a field that changes as quickly as AI does. NVIDIA's strategy is clear: to lead the way in computing towards a more unified, efficient, and powerful future, ensuring that investments grow and adapt, potentially transforming the way the world works. The Grace Superchip server, focused solely on CPU power, can host up to 4 CPUs or 2 of its superchips, boasting that it delivers great performance while using much less energy. It claims to use only 580 watts, half of what similar x86 servers use, which is 1090 watts. This makes it an attractive option for data centers that need to save on power but still want strong performance. The discussion shifts to how networks within these centers are becoming the backbone of operations. There are 2 main types of data centers. The first is the hyperscale data center, which handles a variety of applications, doesn't use many CPUs or GPUs, but has many users and loosely connected tasks. The second type is the supercomputing centers, which are more exclusive, focusing on intensive computing tasks with tightly linked processes and fewer users. Ethernet connectivity is highlighted as a key component that has shaped the development of the internet, thanks to its ability to link almost anything effortlessly. This attribute is essential for the widespread and diverse connections across the internet. However, in supercomputing data centers, where high-value computations are the norm, this kind of random connectivity is not feasible. In these settings, where billions of dollars worth of technology is at stake, connections need to be carefully planned and managed to ensure optimal performance. The flexibility of Ethernet, while revolutionary for the internet, must be more controlled and precise in these high-stakes environments. Networking throughput is vital in high-performance computing, essentially worth $500 million. It's crucial to note that every GPU in the system needs to complete its tasks for the application to progress. Normally, all nodes must wait until each one has processed its data. If one node is slow, it holds up everyone else. The challenge is how to develop a new type of Ethernet that integrates with existing systems while enhancing performance to meet high demands. This new Ethernet would need to be designed to handle large amounts of data and synchronize activities across all nodes effectively, preventing delays caused by any single node. Let's dive into the networks that support these powerful computers. The practical limits of self-managing networks. Such innovation isn't just about meeting current needs, but about advancing network capabilities. The difficulty lies in the technical development and in ensuring compatibility with older systems, which millions depend on. Introducing this advanced Ethernet would transform high-performance computing, making it more efficient. However, this improvement depends on both technological advancements and a shift in how we view and implement network systems. Embracing this change requires investing in infrastructure that supports long-term technological growth. Adaptive routing is promoted as a smart solution for modern data centers. It aims to manage data traffic by detecting which parts of the network are overloaded and automatically sending data through less busy routes. The idea is that this process happens without the central processing unit intervening. On the receiving end, another piece of hardware known as BlueField 3 puts the data back together and sends it off to the GPU as though everything is normal. Then there's congestion control, which is somewhat similar to adaptive routing, but focuses more on monitoring the network to prevent any part of it from getting too congested with data traffic. If a particular route is too busy, the system directs the data to a clearer route. However, the effectiveness of these technologies in real-life situations is often not discussed in detail. How well can these systems truly operate without human help? The promise of no CPU intervention sounds great, but is it really practical, or just a way to sell more advanced and perhaps not always necessary technology to data centers? While the concept suggests a network that manages itself, avoiding traffic jams on its own, there are likely many practical challenges that aren't addressed. Real-time data traffic can be complex and might still need some traditional handling to ensure everything runs smoothly. New solutions are constantly presented as the ultimate fix to long-standing issues. One of the latest innovations is a sophisticated system designed to manage network traffic through a combination of advanced software and switches. This system promises to significantly enhance Ethernet performance by directing the flow of data more efficiently across data centers. The idea is to prevent network congestion by having the system act as a controller, instructing when to halt data flow to avoid overloading the network. This sounds promising on paper, yet those familiar with network management understand that the real-world application often falls short of theoretical models. Meanwhile, a separate discussion has been gaining momentum about the potential of GPUs overtaking CPUs in handling artificial intelligence tasks. Proponents of this shift highlight the superior data processing capabilities of GPUs, which can handle multiple operations simultaneously, making them ideal for certain types of computations required in AI. However, this enthusiasm often overlooks the nuances of computational needs, where CPUs might still hold an advantage due to their general versatility and efficiency in sequential task processing. Amidst these technological debates, there's an unusual confidence placed in a single software stack, touted as the only option secure and robust enough for enterprise use. This claim suggests a one-size-fits-all solution to diverse corporate security and operational requirements, a concept that oversimplifies the complex landscape of business technology requires. Such a sweeping endorsement can lead to an over-reliance on a single technology, potentially sidelining other viable options that might better meet specific organizational needs. As these discussions unfold, it becomes clear that while advancements in technology offer potential benefits, there's a gap between the ideal outcomes presented and the practical challenges of implementation. This disparity is often glossed over by those eager to promote the next big solution. In reality, integrating new technologies into existing frameworks presents a multitude of challenges, from compatibility issues to scalability concerns, which can dilute the effectiveness of even the most promising solutions. Thus, while the allure of new technology is undeniable, a realistic perspective is crucial. It's important to temper excitement with a critical evaluation of how these technologies perform outside controlled tests and in the diverse environments they're intended for. This approach ensures a more grounded expectation and a better understanding of how technology can genuinely contribute to advancements in data management and AI processing. Where security, management, and support are key, NVIDIA's latest move is quite bold. The company has announced it will take care of over 4,000 software packages, covering everything from data processing and training to optimization and making decisions based on data. This mirrors what Red Hat has done for Linux, but NVIDIA is applying it to all its own software, aiming to provide a comprehensive, top-tier service for businesses. Let's consider what this really entails in the realm of accelerated computing. NVIDIA AI Enterprise is not just offering a broad range of tools. It promises to manage and maintain this extensive suite with a high level of care, akin to well-known enterprise services. The challenge here is immense. How will NVIDIA ensure smooth integration across such a wide variety of software? Can they truly deliver the personalized support that big businesses need without becoming cumbersome and complex? We continue exploring how these changes affect who controls technology: AI, NVIDIA, and the new power dynamics of technology. While potentially making things easier by reducing the hassle of handling many software tools, this strategy also brings up concerns about flexibility and being tied to one vendor. Companies are pushed toward a more uniform computing environment, which might limit innovation from smaller software creators and reduce the variety of technologies that could lead to major new discoveries. NVIDIA's claim of offering a business-grade solution is both a sign of their dominance in the market and a strategic move to embed themselves deeply into the operations of their customers. As companies increasingly rely on fewer providers for their computing needs, one must wonder if the future of business computing will be shaped more by technological innovation or by the controlling influence of a few powerful companies. The promise of faster computing through GPUs is often highlighted as a major benefit for enterprises. We're told that using NVIDIA's AI Enterprise on GPUs can process 31.8 images per minute, which is 24 times faster than traditional CPUs, and it costs only 5% of the usual amount. But there's a catch. This impressive boost in speed and cost saving isn't available to all businesses. The key to unlocking these benefits is a secure software stack from NVIDIA AI Enterprise, now fully integrated with big cloud providers like AWS, Google Cloud, and Microsoft Azure. This might seem helpful, but it also raises a question. Is this integration meant to spread advanced computing, or is it a strategic move to make NVIDIA's technology a core part of business infrastructure, making it hard to choose anything else? Let's look closer. The enterprise world is often tempted with stories of how new technologies can change everything. But what's really happening is not just about improving technology, it's about changing who has control in the tech industry. NVIDIA isn't just selling faster processing. They're creating a new dependence. AI needs a different way to handle tasks, and this isn't just about better technology, but about shifting power within the industry. This transformation is driven by two main things: faster computing and AI that can create content. These are supposed to redefine what machines can do. However, with all this talk of innovation, one has to think about what it means when these technologies are mostly controlled by a few big companies and NVIDIA. Their integration into major cloud platforms doesn't just make things easier, it might also lock advanced capabilities behind the doors of these big players. As these systems become more interconnected, businesses might enjoy the immediate benefits of speed and efficiency, but could end up losing much of their control over their operations. This trade-off is often overlooked amidst the exciting stats and promises of change. NVIDIA's collaboration with 100 other software companies under NVIDIA Enterprise isn't just about technical partnerships. It's about weaving a network that might be difficult to escape from. While everyone is focused on the advancements in speed and AI, businesses need to understand the full picture. In a world where fast computing and AI skills are seen as key to success, the real challenge might be about who controls the technology that drives these advancements. A notable shift was taking place in the evolving landscape of technology. Traditional computing, once dominated by general-purpose machines, was making way for a new paradigm that integrated the entire system right up to the scale of data centers. These were not just clusters of machines, they were comprehensive systems crafted specifically for various industrial sectors. Each sector now boasted its own customized software stack, tailored to maximize the efficiency of these colossal computing entities. One of the central pieces of this transformation was the HGX H100, heralded as the core of generative AI technology. Its purpose was straightforward: to enhance efficiency and drive down costs, purportedly delivering unmatched value. This technology was destined to serve AI factories and was augmented through the Grace Hopper system. This system was connected to a vast network, an assembly of 256 nodes, culminating in the creation of the DGX GH200, the largest GPU ever constructed. The ambitious objective was to usher in a new era of accelerated computing that would permeate various industries. The vision didn't stop at merely enhancing AI factories or large-scale operations. It extended its reach into the cloud to transform every cloud data center into a generative AI powerhouse. This endeavor was propelled by Spectrum-X, a system that was foundational to this transformation and depended on four essential components: the switch, the Bluefield 3 NIC, the vital high-speed interconnects, including the indispensable cables, and a comprehensive software stack that orchestrated the entire operation. The strategic ambitions stretched even further, aiming to penetrate global enterprises with a variety of server configurations. This expansion was facilitated through strategic partnerships with Taiwanese technology leaders, leading to the development of MGX modular accelerated computing systems. These systems were designed to integrate NVIDIA technology seamlessly into the cloud, enabling enterprises around the globe to implement generative AI models in a secure and efficient manner. As this technological revolution unfolded, it was becoming clear that the shift toward tailored, industry-specific computing frameworks had significant implications. While the promise of enhanced performance and cost savings was enticing, it also increased the dependency of companies on specific technologies and vendors. This burgeoning reliance could potentially restrict flexibility and stifle innovation in a market known for its rapid evolution. Despite these concerns, the drive towards specialized, comprehensive computing environments continued to redefine the approach of businesses toward technology utilization. The integration of advanced technologies with commercial strategies was shaping a new era in business computing, influencing how enterprises leverage technology to achieve their goals. The journey was complex and filled with challenges, but the potential rewards promised a new frontier in efficiency and capability in the business world. What are your thoughts on the risk of stifling innovation due to increased dependency on specialized technologies? Comment and subscribe to join the discussion.